one more section. One more to do. So less material on this test, so that's a good thing, maybe. Okay. I've almost got the practice test finished. I should have it posted later this afternoon. Okay, so it'll be up. Okay. So since just 4 sections, it's kind of less critical for us to have that, but I should have it up though. Okay. All right. So this section is not really tied to the other topics in this chapter. It could be put a lot of places in calculus class. Just we need to have done limits, and we need to have done derivative rules, basic derivative rules, and then we could do this section. But it's got to be put somewhere, so this is where it got stuck in this textbook. So that's where we'll cover it. Okay. So we're back to taking limits. Okay. So we are kind of going back to here, but we're dealing with special circumstances. Okay. And those special circumstances are what we call indeterminate forms. We have seen a couple of situations where we could deal with indeterminate forms and limits already. Those are when if we try to use direct substitution with a rational function, then we may get in a situation where we get 0 over 0. We can't calculate that, so we call that 0 over 0 indeterminate form. Okay. You can end up with the same thing if you're approaching infinity. You can get infinity over infinity, and we don't have a way of calculating that. Okay, so that's another example of indeterminate form. So this thing we're going to look at, okay, and this French guy's name, okay, it's like Le Hopital or something like that. Okay, in Alabama, it usually gets called L'Hopital, so that's what we're gonna say. Okay. L'Hopital's rule. And the sad thing about it is the guy's name is hard to pronounce, and he's not even the one that came up with it. They got named after him, but he just stole it from somebody else. So it's easier to me to call it Bernoulli's rule, but nobody calls it that. He stole it from, well, he didn't steal it, but he used it from one of the Bernoullis, and he got credit for it. But anyway, all right, here's our situation. Okay. We've got some kind of function. Maybe we want to know the limit of this thing as x approaches 1. Okay. If you think about direct substitution, okay, we run into a problem right away, because in the denominator we get 0. Okay. But also, if we try to plug 1 into the top, we try to take ln of 1. So natural log of 1 means e to what power would give you 1. So that is 0. Yeah, so we would end up with a 0 over 0 situation. We can't calculate that, so we call that a 0 over 0 indeterminate form. Okay, that's our situation. Okay, there are other ways you can run into that same thing. Okay, so anytime if we tried to use direct substitution, if we would end up with 0 on top and 0 on the bottom, we can call that indeterminate form. And we have had some examples of that we could deal with special techniques that apply to those circumstances. We're after a more general solution here. Okay. So like this is what we've seen before. If we look at this limit, x squared minus x over x squared minus 1, if we look at that limit as we approach 1, if we try to use direct substitution, we'll get 1 minus 1, 0 on the top. In the bottom, we get 1 minus 1, 0 on the bottom. So we have had that indeterminate form before. The situation we were in before, we could factor the top and the bottom. and then we've got some cancellation that happens. And so here the x minus 1s would cancel out. And then it worked out nicely where if we tried to plug in a 1 then we would get 1 over 2. And we got our answer. Okay. We even briefly in here, talked about using something like the squeeze theorem. Okay. To find this limit, we say if this function is always bounded by two other functions, okay, and the limit of the upper function and the limit of the lower function is the same at some value, at 0 on this one, then the limit of the one in between has got to be the same thing. Okay? We didn't spend much time there, but we looked at it briefly. Okay. And we also ran into infinity over infinity situations. We'll see those in a second. Okay? But yeah, okay, so we got infinity here. Okay. So what's going on with this one? If we are approaching infinity on the bottom, we get infinity minus 1, which would just be infinity. On the top, we've got natural log of infinity, but even though the natural log grows really slowly, it does tend toward infinity. Okay. So in this case, we have infinity over infinity. Okay. So that's another indeterminate form. And we did, make sure we go, yeah, we did deal with those a little bit as well with rational functions. So we had the situation where if we had an infinite limit of a rational function, we could divide everything by the biggest power of x in the denominator. And then we do that, we said 1 over some power of x as we approach infinity is 0. So that one, we can figure out our limit was 1/2. Okay. But okay, we can't always do that, right? With natural log, nothing we can factor out of that really, so we need some other technique. Okay. That's where L'Hopital's rule comes in. Okay. So here's our rule. Okay. All right, so we need a ratio of two functions. Okay, so f and g here, and we need them both to be differentiable. So we need to be able to find their derivatives, and then we need the derivative of the bottom one not to be 0, at least around whatever value we're approaching a. Okay. Okay, then, if we're in the situation, this part's the important part. Okay. If we're in the situation where we have an indeterminate form, okay, so 0 over 0 or infinity over infinity, then we can use L'Hopital's rule. And what L'Hopital's rule tells us is that the limit of the ratio of the two functions is the same thing as the limit of the ratio of the two derivatives. So essentially what we're doing is if we have an indeterminate form when we've got f over g, we take the derivative of f over the derivative of g, and that's going to be the same limit. Okay, it's going to be the same limit. Okay. Importantly, we've got to be an indeterminate form before we use L'Hopital's rule. Okay. If you just have some rational function and you try to just jump straight into L'Hopital's rule, and we're not in indeterminate form, then you're probably going to get the answer wrong. Okay. Every once in a while you'll get lucky and it comes out the same both ways, but more often than not, you get a different answer. Okay. You got to make sure you're in indeterminate form before you do L'Hopital's rule. So let's look at one. That's showing you why it's true. Okay, here's our first example we'll go with. So we got ln of x over x minus 1 as we're approaching 1. So let's just go to scratch paper and do this thing. actually doing L'Hopital's rule in my high school seniors also, but it's like the last thing we're doing. So different places in different books. So, all right. Here's our problem. We want this limit. Okay. So we said we need to verify. Okay. If we just try to use direct substitution, okay, this thing is going to give us a 0 over 0 indeterminate form. And that is important. We cannot apply L'Hopital's rule if that is not the situation. Or we can, we'll just be wrong. Okay. So L'Hopital's rule says this limit has got to be the same thing as the limit of the derivatives of these. So what's the derivative of natural log of x? You remember? 1 over x. Yeah, 1 over x. So take the derivative of the top. And then the derivative of the bottom is a little bit easier. It's just power rule, right? We just got x minus 1. So our derivative on the bottom is, yep, 1. Okay. Now if we try direct substitution, we can do it. So this will be the limit of, as x approaches 1, of that. So that's 1 over 1 over 1. So we don't need the limit there. So what's that going to be? 1. So we used L'Hopital's rule. We took the derivative of the top, the derivative of the bottom. That got us out of indeterminate form. We could just use direct substitution, and then we get our limit. Okay. So L'Hopital's rule by itself is not difficult. Okay, the only thing that makes it difficult is if you have something nasty to take the derivative of. We're going to try to avoid that as much as we can. And if we just focus on knowing the rule, okay, and when it does. Okay. So let's see. Let's look at another one. Here's another limit. So as our x values get large, what's going to happen to e to the x? What's it going to approach? Infinity, yeah. So bigger the x values, the bigger e to the x is. We look at the denominator. As our x values get bigger, what's going to happen to x squared? It goes toward infinity as well. It goes toward infinity as well. So in this case, we're in infinity over infinity indeterminate form. So different indeterminate form, but we do it the same way. We do it the same way. L'Hopital's rule applies here. So L'Hopital's rule says that our original limit is the same thing as the limit of, take the derivative of the top, so the derivative is e to the x, okay. And on the bottom, the derivative of x squared, 2x. Okay. Now if we think about this one, we've already established, right, that e to the x is going to go toward infinity, so we've got infinity on the top again. On the bottom, we've got 2 times some large number. What's going to happen there? You're still going to get infinity. That's okay. Right? There's nothing that says we can only use L'Hopital's rule one time. Okay? Now we're in the same situation. We got a different function, but we're in the same situation when we got infinity over infinity again. Take it again. Yeah, use L'Hopital's rule again. Okay. Nothing wrong with that. You can use it as many times as you need to. You just have to make sure each time that the thing you're starting with is in indeterminate form. If it is, use L'Hopital's rule. Or feel free to use it. That's not always the thing to do, but it is a thing to do. Okay. So now take the limit of the top, get e to the x. And not a lot of progress on that part, but take the derivative of the bottom, 2. Get 2. So now what's going on? We know as x approaches infinity, e to the x is going to give us infinity for the limit. But on the bottom, we don't even have an x, so we don't even care what that's approaching on the bottom. We're just going to get 2. So this thing, what's our limit going to be? Infinity divided by 2. You can't actually do the calculation. We can think about it and reason it out. You know, if you have infinity and you divide it in half, what do you end up with? It's still infinity. Yeah, a little mind bending, but yeah. You have some gigantic number that you can't even imagine, and you divide it by 2, it's still a gigantic number that you can't imagine. It's still infinity. Okay. The thing you have to be careful of, okay, is don't use L'Hopital's rule again. Okay, because when we're right here, that's not indeterminate. Okay. So we can't use L'Hopital's rule again. If we did on that one, we would just end up in a mess anyway, because we would have infinity over 0. Okay. And that's like just asking for trouble. But don't do it again. Okay. All right. So there's a few examples there. That's not the limitation of L'Hopital's rule, because there are other indeterminate situations we can find ourselves in. Okay. So the ones where L'Hopital's rule directly applies, your 0 over 0 and infinity over infinity. But we can have other situations where we have an indeterminate situation as well. Okay. So here's one. Okay. What if we have this situation? We try to do 0 times infinity. That one may be a little counterintuitive. You may be able to make an argument in some situations that that would be 0. But in general, it's indeterminate, okay, because we're not actually multiplying. So we have to think about it conceptually. 0 is already a hard concept. You think about it hard enough. And infinity is conceptual as well. So you could run into that. In that situation, let's one way we can get around that, okay, is, and they kind of skip a step when they're writing this to me. I mean, at least from the way we've been thinking about it. So if we've got f times g and we're getting 0 times infinity, we can rewrite this either way. We could write it like f over e to the negative 1. Okay. And that would give us, if you simplify that, f over 1 over g. Just move 1 to the bottom or you write it that way. Okay, so like in this case, if the limit of f was 0 and the limit of g was infinity, and when you do that, you would get 0 on the top, and you would have 1 over infinity. What would that limit be? 0. So then we've got it in 0 over 0 form. We can use the L'Hopital's rule. Okay? Same thing applies if you switch it around. Okay, you could either get 0 over 0 or infinity over infinity. It just depends on how you manipulate it. Okay? So let's look at one where that's useful. Got the limit of x times ln of x as x approaches 0 from the right. Okay? L'Hopital's rule still works for one-sided limits. Okay? So, no big deal there. Let's go over to our scratch paper here. So we want the limit as x approaches 0 from the right of x times ln of x. Okay? So what's going on this one? So as x approaches 0, what's going to happen to x? Don't think too hard about it. Yeah, so this one's going towards 0. Yep. And then as x approaches 0 from the right of ln of x, we might have to think about that one a little bit more. What's going on that one? You may remember what the graph looks like. The graph of the natural log of x. This. So as we approach 0 from the right, what's happening to the natural log of x? Going to negative infinity. So I know we've got negative infinity instead of positive infinity, but it's the same situation. And we've got a 0 times negative infinity situation here. Okay. So we want to rewrite this thing in a way that we can use L'Hopital's rule. Okay. You can move either one to the bottom, but one choice is less messy than the other. The preferred way of doing this one, got some extra, I don't know what letter that was, it wasn't an M anymore, it had like 5 humps on it. Would be to write ln of x, leave it on the top, and then we'll have x to the negative 1 in the bottom, which is 1 over x. So then now, as we approach 0 from the right, we said the top's going to go to negative infinity. That hasn't changed. Then what's happening on the bottom? 1 over x. But as we go towards 0, what's happening to 1 over x? Yeah, what's that graph look like? That's like, yeah. So as we approach 0 from the right, going toward infinity. And that's okay, the signs are different, that's all right. So here are our tops going toward infinity. Yeah. No, going toward negative infinity. bottom's going toward infinity. That's indeterminate form. The sign's not important for that part. Okay. Just to make it explicit, this is not -1. Okay, it's like infinity over infinity is not +1. Okay. So now we're in indeterminate form, so I can use L'Hopital's rule. Okay, use L'Hopital's rule. So, and this is the reason why which one you move makes it messier or not. Okay. Now we need to take the derivative of the top and the bottom. So we said the derivative of ln of x is 1 over x. And then what's the derivative of 1 over x? So 1 over x is x to the -1. So if we take the derivative and give us -1 x to the -2, that's -1 over x squared. So now what? Now we've got a little algebra rearranging to do. Like that looks like that hasn't helped because this one's infinity, this one's negative infinity. But what can we do? What can we do? Yeah. So yeah. Yeah, a couple ways you can think about it. You can think about it from the perspective of simplifying a complex fraction, right, where you flip the denominator and multiply, or maybe more in line with how we've been thinking about exponents in this class most of the semester. So that top x to the -1, the bottom's negative x to the -2, and we could just use our exponent rules. So what's our rule if we've got a quotient? Yeah, we subtract the exponents. You have to be a little careful because of all the negative signs. So we got -1 minus a -2. That's -1 plus 2. It's 1. And it's now what's our limit? Use direct substitution. 0. -0, which is 0. Yeah, -0, yeah. This is 0. Yeah, -0 is 0. So a little work on that one. Kind of a little messy, but get there. Anytime when it's not just directly in 0 over 0 or infinity over infinity, it makes them messier because you got extra steps you got to add in. And then that one was because of simplifying this part that was a little extra messy. Let's look at another one. It's similar. but we got some different things going on. This one's not a product one, so we don't have to rewrite. We're already in indeterminate form. What kind of indeterminate form are we in? Natural log of infinity. Takes a long time to get there, but it goes to infinity. Square root of infinity, even though you're taking the square root, it's still infinite limit there. So we're in an infinity over infinity situation. Hey, those are ugly. So we can use L'Hopital's rule. Take the derivative of the top and the derivative of the bottom. Okay. Derivative of the top, we've seen it plenty of times today. 1 over x. The bottom, it's easier to think about it as x to the 1/2. Okay. So what's the derivative of the bottom going to be? Yeah. If I can write 1/2 x to the negative 1/2. Okay. Trying to think our way through what that denominator would give us now is a little bit tough if we don't get rid of the negative exponent. So maybe it's a little easier to think about if we write it like this. That's 1 over x over 1 over 2 square root of x. Move that to the bottom there. So 1 over infinity is going to be 0. Because we're on the positive. Yeah, it's 0 both sides. Don't think about this the other way. And then even though we take the square root of infinity, multiply it by 2, that's still going to give us a 1 over infinity situation. So 0 there. So what situation are we in now? 0 over 0. Okay. So we could try L'Hopital's rule again. I'm actually thinking maybe that's not our best bet on this one. Let's look. What happens if we do L'Hopital's rule again? So x to the negative 1. So derivative of our top would be negative x to the negative 2. And then derivative of the bottom, we'll get negative 1/4 x to the negative 3 over 2. We're going to find ourselves in the same situation. So what's going to happen there if we just try to do L'Hopital's rule, we're just going to be in a loop, well, not a loop, but we'll just be doing L'Hopital's rule until we give up. Okay. So maybe there's a better way of going about that one. Oh, yeah. Do the same thing we did last time. Because we were in that similar situation last time, right, when we were here. we just had to do some algebraic simplification. This one's a little bit more convoluted because we've got the square root involved. Maybe it's easier to think about dealing with this as a complex fraction this time, so we would flip the denominator and multiply. And get 2 x to the 1/2 over x. And then when we simplify that, what's that going to give us? I'm not thinking about the limit, I'm just thinking about algebra here. Yeah, you're right. So we got 1/2 minus 1. We got 2x to the negative 1/2, which is 2 over square root of x. So kind of had to do that right off to the side just so we didn't get lost in our process here. That we can find. Because this is not indeterminate anymore. We've got 2 over infinity. It's been a while since we've done those. You remember if we have a number over infinity? Number over a power of x? Yeah. That is 0. See? So if you find yourself in a loop of L'Hopital rule, try to look back and see if there's a step where you could rewrite it without using L'Hopital's rule to get you out of indeterminate form. Okay. Yeah, indeterminate, yeah. And really directly, you can only use L'Hopital's rule when it's 0 over 0 or plus or minus infinity over plus or minus infinity. But we had the one where we started off 0 times infinity indeterminate form, but we rewrote it to make it infinity over infinity. Yeah, so this is a good time. Give us a little break from all that algebra. So think about this one. What situation are we in there? We use direct substitution. What do we get? 0 over 2. So we just get 0. That's not indeterminate. If we tried to use L'Hopital's rule, like maybe we were halfway checking and we said, oh yeah, if I plug 1 in the top, I get 0, and then we didn't check the bottom. And if we tried to use L'Hopital's rule, I'm going to put not equal to because we know it's not right. If we try to use L'Hopital's rule, we do the derivative over the derivative. Derivative of the top over the derivative of the bottom. So derivative of the top is 1. Derivative of the bottom is 1. The way we get 1. And we would be wrong. We would be wrong. Okay. So you got to check the top and the bottom. Okay. If we switch these, so I don't get in the habit of just checking the denominator either. Well, yeah, I should just change it to -1 instead of actually switching them. Okay. Different situation, but we're still not in indeterminate form here. Okay. So on top we would get -2 On the bottom, we would get 0. We can't use L'Hopital's rule here because it's not indeterminate. It's not indeterminate. What is it? Do you remember the situation? So this one, it's like really easy. It's just that we hadn't talked about it in a while. If we try to do direct substitution, we get -2/0. Okay, that doesn't work. So then our strategy in the past would be, okay, let's see if we can factor and cancel something out. We can't. And we also can know that because we don't get 0 on the top. If we're having something non-zero over 0, yes, there's an asymptote there. So this limit does not exist. So either situation, 0 on top, 0 on the bottom, neither way do we get 1. Okay. So L'Hopital's rule doesn't work here because we're not in indeterminate form. Okay, one more little situation here. Most of these are straightforward. You start off in 0/0 or infinity in the assignment. Okay, so not a whole lot of having to do ones like that where we had 0 times infinity. There is one other situation we're going to talk about. There's actually probably like 8 indeterminate forms, maybe more than that. We're not going to cover all of them, just the main ones. So here's the last situation we're going to look at. That's when we have infinity minus infinity. Okay. Tempting to say that's 0, it's not. We can actually subtract. Okay. So we need to if we have one in this situation, we need to rewrite it somehow. So we end up in 0/0 or infinity over infinity form. Okay. Here's one example. This one's a little messy again. Here we've got approaching 1 from the right, 1/ln of x minus 1/x minus 1. So let me transfer that over to scratch work here. The textbook walks through that one, but they just leave some algebra steps out that are not super clear, in my opinion. Okay, so what was it? 1/ln of x minus 1/x minus 1. Okay. So that's 1/0 if we do direct substitution, minus 1/0. And those limits, since we're approaching 1 from the right, those limits would be infinity minus infinity. Okay, so we're in infinity minus infinity situation. And that is indeterminate. So one way we can go about this one is to get a common denominator. Our common denominator is not all that hard to get. It's just ln of x times x minus 1. Or x minus 1 times ln of x. So what that gives us x minus 1 over ln of x minus, oh, I left out the term. So we have to multiply the first one by x minus 1, so we get x minus 1 at the top. We have to multiply the second one by ln of x, so we get x. Okay. We try to do direct substitution. Let's walk through it. It's a little more complicated here, but we plug in 1 there and 1 there. Then we got 1 minus 1, 0 minus 0. So that's 0 on the top. The bottom's a little bit easier. If we try to plug in 1, we get 0 times ln of x, whatever. We don't even care what that is. It's going to be 0. So now, what can we do? Use L'Hopital's rule. Okay. And it looks worse than this one is. This derivative is not as bad as it might appear. Especially on the top, the derivative of x is 1. The derivative of minus 1 is 0. And then we got minus the derivative of ln of x, which is 1 over x. The bottom's a little bit worse because we've got product rule. It's the derivative of the first term, so x minus 1, so that's just 1 times ln of x plus the first one, x minus 1, times the derivative of ln of x, which is 1 over x. And we don't have to have this 1, so I'll just get it out of there just for tidiness. And a few different ways you could go about simplifying this thing. Again, we've got this complex fraction situation. One way that's pretty nice that you may not remember from algebra class, but we can multiply through by the least common denominator of all the fractions we have, which on this one's easy because the only denominator we have like inside is x, so we can multiply everything by x. That'll get rid of the complex fraction situation. The book's not real clear about what they're doing there, so it's kind of looks like magic. So 1 times x is x. 1 over x times x, 1. ln of x times x ln of x. And then x minus 1 times 1 over x times x. The 1 over x and the x cancels out. Get that. Now let's see. What situation are we in now? try to do direct substitution. Zero over zero. Sadly. Okay. So we gotta do one more go around. Okay. Do one more go around. It pays off on this one, and we don't get stuck in just doing the L'Hopital's rule. So derivative of the top, 1. The bottom's a little bit messy because we got that x times the ln of x. So we got to do a product rule. So derivative of x is 1 times the ln of x plus x times derivative of ln of x is 1 over x. The derivative, so I'm got that part done. Yeah, plus 1. And then 0 for the minus 1. Good news about that. We're almost there. Yeah, it turned into 1. So we get ln of x plus 1 plus 1. So we get plus 2. And now, thank goodness, we try direct substitution. Get 1 on the top, so not indeterminate anymore. And then the bottom, ln of 1 is 0 plus 2. So finally, we get our answer. It's 1/2. They're not all that bad, I promise. One more little trick. This one's not so bad. This one's not so bad. So e to infinity is going to give us an infinite limit minus infinite limit. So we're in an infinity minus infinity situation. And this one, a nice little trick that helps sometimes is we're going to factor out an x. It's not obvious. Okay? That's why I'm showing it to you. Okay? Factor out an x. So if we do that, it's a little weird on the first term. So we need it to be when we multiply x by our first term, we get e to the x. So the way we do that is we have e to the x over x. That way, when we multiply, the x's cancel and just get e to the x. And then factor out of x and get minus 1. The one kind of inconvenient thing on this is the limit as we approach infinity of e to the x over x gives us infinity over infinity. So what I'm going to do, I'm going to break that part out separate. After you get that answer, this is a nice problem. Okay? But we need to figure out what to do with that part. That's infinity over infinity, so we can use L'Hopital's rule. So take the derivative of e to the x, that's e to the x. take the derivative of x, that's 1. So then what's that limit going to be? It's just e to the infinity, so that limit's going to be infinity. So now, okay, it's unfortunate that we need L'Hopital's rule inside of a L'Hopital's rule problem. Okay. But other than that, once we can see that e to the x over x as we approach infinity is infinity, this thing's nice, because now what situation are we in? Infinity times infinity minus 1, which is just infinity. So, situation we're in here is infinity times infinity, which we've been talking about all these indeterminate forms, so it makes you want to say that's indeterminate, but it's not. That's infinity. Yeah. That we can figure out. If we have a huge number times a huge number, what are we going to get? A huge number. Okay. That one's infinity. Okay. All right, so just a quick mention, you don't have any of these problems, so don't freak out. Okay. Just so we can say we did. We have this situation where we got a limit of a function raised to another functional power. So that's like a easy example there would be like x to the x, or if we had like e to the x squared or something like that. We can get in other indeterminate situations like the limit of 0 to 0 or infinity to the 0th power, or this one you might not even think about being indeterminate, but we're thinking about the limit of 1 to the infinity power. It's just that we've got the infinity power that messes that up. And just to mention, okay, we're not going to deal with any of these, okay, but just to mention the trick that you use on most of those where you've got indeterminate exponent situation, okay, is that we end up taking the log, and then we can move the exponents up front. And they are pretty messy. Sometimes. So, like, we're not doing it. Okay. Like, we got this, and what we could do is we could take the log of both sides, okay, and then deal with it from there. And we're not going to just because they get a little ridiculous in there, but you could do that. We didn't do a lot of logarithmic differentiation either, right? So just a little. There. Okay. What happens is you end up getting it in 0 over 0 or infinity over infinity form, and then it's the same story as what we've been doing. Okay? That's all. Okay? Not many too bad ones in the assignment. Okay. All right. Yep. So we'll review Friday, test Monday. But it's only 4 sections. So